Scientific notation and measurements. So measurements are quantitative. They're more than just numbers, and you have to make sure that you communicate this. So measurements report specific quantities, and I'm going to abbreviate. You're welcome to abbreviate as well. Quantities represented by common units. Nearly every measurement is a number plus a unit. This is a big deal. If you leave your units out in college or even on the AP exam next year, your answer will be either totally incorrect or they will take points off for that. So you always have to remember your unit. As I said up here, you're never going to have like a recipe that's just going to say add 1 salt, 2 sugar, and 3 flour. You've got to have 1 teaspoon of salt or a cup of sugar. So just think of it that way. You've always got to have that unit of measurement. And just for a definition, a unit of measurement compares what is to be measured with a previously defined, standardized, that's important, size. So when you're looking at our balances in particular and specialized equipment, they all have to be calibrated in order to be set to the standardized size. That's what those little weights are for that you'll see in our glass cabinets. They're for calibration. So we have some examples here: foot, inch, meter, pound, gram. A foot length was used centuries ago to mark off distances, but it didn't work very well because everyone's feet were different. So we had to finally come to agreement about what a standard foot length and measuring would be. And so that's when rulers began to be developed. Scientists all over the world have agreed upon a single measurement system called the System of International Units, which you will need to become familiar with if you're not already, of international units. You'll not see it like this, though. You will see SI units. And that's how you'll want to talk about this as well. So you will see SI base units. There are 7 units representing different types of measurement. And you will need to know all of these and their symbols. So we've got length, which is a lowercase l. Mass is a lowercase m. Time is a lowercase t. Temperature is a capital T. Now that's why you have to be careful about whether you're doing lowercase or uppercase. If you're trying to communicate temperature and do a lowercase, your formula is now telling someone to insert time, and that's really going to mess with people. Amount of substance is a lowercase n. And then I've just already filled out electrical current and luminous intensity because we really don't use those at this level, but they are there for you to know and to have been exposed to. The unit name for length, the SI base unit, is going to be meter, and that abbreviation is a lowercase m. The unit for mass that we use is the gram, lowercase g. Time is the second, lowercase s, and you will also see it like this sometimes. Our textbook didn't have that, but I've seen it like that on multiple occasions. Kelvin is the SI unit for temperature. We will learn how to convert Celsius and Fahrenheit to Kelvin. And then the amount of substance is something called a mole, which we will also learn about, and it is abbreviated that way. Again, you will need to know these. Just expect that this will be on your quiz. I will have this ready for you to fill out. I'm not going to worry about putting those on the quiz, but these you will need to know. So in order to communicate really, really large numbers like this, or really, really small numbers like this, like this, you need to be able to use the SI base units along with prefixes. The prefixes are what allow us to go really big or really small. They are just added to the base units. To base units to represent quantities that are larger or smaller. And so we start with our base unit. That's what you are being asked to memorize to start with and what that means. So we've got 1 meter. Now if we want, let me move this over. If we want to communicate more than 1, we're going to go this direction. Less than 1's going to go this direction. So that's how this works. And so we have mega, which is a capital M. We have kilo, which is a lowercase k. I'm going to put a star by that. You see that a lot. Deca, I really haven't seen it used much, if ever, in the real world, but it's there and you'll know what it is just in case. And then we start to go less than 1 into deci, which is a lowercase d, centi, lowercase c, milli, lowercase m. Now, those you're going to see a lot. And micro. You actually, I used micro quite a lot when I worked in the environmental sector, and its symbol is a mu. Now it looks like a U that's just been squashed. It's kind of like that. Okay, it's a Greek letter. You actually will see that a lot if you end up in some sort of science after high school and college. So I'm going to actually star that one, and it's usually communicated, instead of micro, they'll use parts per million. Nano is another one that you'll see, especially if you end up in the environmental sector. It's a lowercase n, and it's usually communicated parts per trillion. Okay, so there is a memory device to help you remember all of these prefixes, and you will need to know them. It doesn't include mega, but it will get the rest of them all the way through milli. And let me change my ink color here. So it goes King Henry. Oh, we left out, okay, Henry. That's for hecto. I'm going to put that here. We don't really, that's not one that's used a lot either, but you need to remember that one. I skipped over it. King Henry died drinking chocolate milk. So that might be helpful. K for kilo, H for hecto, D for deca, D for deci, C for centi, and M for milk. That's just a little mnemonic to remember that. So let's say that you want to use that to convert 45 meters to kilometers. So you would go over here. Meters are your base unit. Okay, right there. and you're trying to get to kilometers, okay, which is up here at the top. So you're going to figure out how far away that is, and that's 1, 2, 3 away. So you're just going to move the decimal place. 1, 2, 3. So it'll be 0.045. So I just wanted to show you this mnemonic one more time. If you write it out sideways, because I realized in that last slide you probably didn't know necessarily which direction to take your decimal point. So if we have the 45 meters and we want to know how many kilometers, this works really well if you need to write it out. There's your base units. Meter, liter, gram are some of the most common ones. So we know we're going from 45 meters at a base unit to kilometers, which is over here. So that shows us that we're moving the decimal to the left however many places. In this case it was 3 places, so it became 0.045. So on the same note, let's do 45 meters and convert that to millimeters. So this time again we're starting right here, but we want to get over here to where we know it's millimeters. So that's going to be 3 spots the other direction. So 1, 2, 3, boom. And just make sure that you know how to do this for your quiz. I will have some simple conversions like that on your quiz over this. So just make sure, if you use King Henry, fine, or if you just memorize it or do note cards, whatever you need to do. Our next little section is just, again, to be able to communicate scientifically to people. Accuracy refers to the closeness of a set of measurements to the exact or to the actual or correct value of the quantity that is measured. Whereas precision is just the degree of agreement between the measurements. So they could be totally wrong, but all be very close and still be precise. However, they would no longer be accurate because, say, for example, your balance was not calibrated or something like that. So the dartboard is a good visual for this. You've got darts all right here, right in the bullseye. That means that you have high accuracy because the bullseye is what you're shooting for, and high precision because they're all a very tight group. Part B here, you've got a tight group of darts. However, they're off away from the bullseye. So what you have there is low accuracy, and high precision. They're precise because they're still very close together in measurement. And then here you've got them all over the board and they're not in the bullseye. So you have low accuracy and low precision. So percent error is another term and process that you need to know. It just compares the accuracy that says accuracy of an individual value or data point or an average with the correct or accepted value. There are lots and lots of tables of accepted values of things like density and so on, that you can compare what you're getting experimentally with accepted values and figure out how precise you've been. And the formula for the percent error is just the value of the experimental point that you got minus the value of the accepted divided by the value of accepted times 100. And that will give you your percent error, and it'll be reported like this. And a lot of the times, this one has a negative, but you will often see this reported as a positive negative 1.9. You'll see that when you're shopping for different types of equipment, or even in the research, like the journal article that I made you do, they might say something is accurate, like plus or minus 1.9 milliliters or whatever. You might see that kind of notation.